All right, and welcome back to class. All right, so today's video is picking up with electromagnets is where we're at. But let's take a rewind for just 1 second to where we were with the last video. The very last thing we talked about was what a solenoid is and like some uses of a solenoid and where you would find them. And essentially we defined a solenoid. A solenoid by itself is nothing more than just a loop of wire. But there is something very interesting. When you actually hook, say you could connect this loop, this solenoid, if you hooked it up to a battery, drawing a very ugly battery here, probably the worst, most unrecognizable battery in the history of humankind. Anyway, if you hook it up to this battery, what you will find then is a magnetic field around the solenoid. You will literally find a magnetic field just like a bar magnet. The exact same phenomena of the field lines coming in, the field lines going out. And so essentially you would end up with a south pole and a north pole on that solenoid. Now that's useful for us because if you took, for example, a bar magnet and you got a bar magnet near this, let's say we had a bar magnet with a north and a south pole, this bar magnet, since you've got opposing poles, this bar magnet would be pulled into the solenoid. So that's how solenoids are essentially used, or can be used as a switch. So say, for example, we talked about in the starter motor on the car, it uses a solenoid, this part that's up here on the top. It pulls this in and actually connects the main supply of electricity to your starter motor. And it also kicks this clutch out to actually activate and spin your flywheel and start the car. We talked about this. This is your solenoid on your ice maker in your house. It actually lets the water go to the ice maker to make little ice cubes. So anyway, well, now let's do this. Let's talk about what an electromagnet is. Well, all an electromagnet is when somebody puts, go down there and take a look at this. When everybody thinks of electromagnet, or at least when I do, I think about this picture. I think about, because I remember as a kid, like getting some wire and wrapping it around the nail. And what you'll notice is the nail becomes magnetized. Well, remember something. You make a coil connected to a source, makes a magnetic field. So that then magnetizes whatever is inside of the coil. And so the stronger the field you can create, so the more coils, the stronger the potential, the stronger the magnet you're going to be able to create. And so essentially you would end up with like a north and south pole on this electromagnet. So I've got some things up here made with an iron core, in this case like a nail and copper wire. They're used in so many things. They're used in motors. And I'm going to do something. I'm marking off the word television because there's not been a television made within the last 10 years that use an electromagnet. Televisions that use electromagnets were, and we talked about this one in the other videos, the old CRT tube, cathode ray type devices, the big thick monitors. They used electromagnets in their production. Circuit breakers, and we'll talk about circuit breakers a little bit more in this video series. Ammeters, and most people know what an ammeter is, especially if you've already been around and you've heard me teach about electricity. A galvanometer is a little bit of a different device. Essentially, a galvanometer can detect even the smallest little currents. So how it works essentially is you take a compass. So let's just say that you took a compass and you had your compass needle, and then you wrapped a coil of wire around the compass. What happens as soon as a current, an I, so you put some kind of a current in amps flowing through that, you would then cause the compass needle to deflect. So say, for example, even in this. So as you look right now, the compass is directed, so let's say north and south. But what happens, and what's cool about this, and this is all a tangent galvanometer is, it's essentially this setup. When you apply voltage to this coil, it's going to make a magnetic field. And so what happens is, let's see if we can just barely move the slider, boom. And if you notice instantly what happened to the compass aligned itself to the magnetic field. Now, This is an extreme example. What's neat when you work with very, very minor currents, this compass will deflect just a little, and keep going. And this is essentially even how an old school ammeter works, is by the same principle of an electromagnet. It's just it didn't deflect quite as easily as this compass. But that's all a galvanometer is. It's basically a compass surrounded with wire. And even one of my favorites, electric guitar pickups. So if you play electric guitar, I've ever been around one, you'll notice something like, say, for example, on a 6-string guitar, you'll notice 6 little pieces of metal. And if you really look, they're just surrounded by wire. And it is an electromagnet. The magnet, actually, it's really awesome how this stuff works. You've got your metal guitar string, and you actually magnetize the guitar string, and then the vibrating guitar string actually induces, that's the new word you're about to learn. It induces a current in the wire, and that's actually where the sound comes from. So while we're talking about that, let's just move straight from guitars into what's known as induction. Because that is how the pickup on a guitar works. It works on the process of induction. So there's your new magic word that we need to focus on. And all induction is, I'm trying to think of how to easily, let's pull up this little example for a second. I'm going to do something. So look at what you've got. We've got a coil, which is, and yes, I know, I'm from Alabama. I cannot pronounce the word coil. But anyway, we've got a coil of wire, a solenoid connecting to a light bulb. Now look, at this moment, there is a magnetic field going through the coil, but there is no light. There's no current. The electrons are not moving. Someone grabbed the bar magnet, and now notice something. Whoa, whoa. What happens if I just stop? And it doesn't matter where I stop. Do you notice what has to be true about the magnet in order to actually create the electricity? The magnet has to be moving. There has to be a changing magnetic field. You can't just stick the magnet in there and expect to have electricity. This is what's known as induction. Whenever you have a changing magnetic field near a coil of wire, you induce, and that's why we use the word induction, you create a flow of current. You actually get these electrons to move within inside the wire. But notice it is contingent upon, now this is neat, notice this. Look at the direction the electrons move. Stick the north end in. Look at that. Now let's come over here and stick the south end in. It's kind of interesting just to see the difference of our direction. This is actually what we're making is let's go super fast, an alternating current. We're vibrating the electrons back and forth and sustaining a flow of electricity. But that is all that induction is. So process by which a moving, keyword moving magnetic field produces an electric current, in a conductor. A conductor needs to cut across the field lines. This is a word that drives a lot of people crazy. They look at this and they're like, what the flux are you talking about, Mr. Cole? Check it out. This word flux. Flux is actually the term. It's actually this. It's a product of magnetic field and area. So flux, and we're not going to solve any problems with this, but magnetic flux, and that is the worst. There, see if I can write that formula better. Flux is equal to B times A. Technically, if we're being picky in our physics, we even have to account for if there's an angle between those. But flux is a product of not just the magnetic field, but the magnetic field in the area that it's in. So say, for example, go back to this little diagram. The magnet is creating the magnetic field, but the flux is actually the product of the magnetic field going into the coil and the area of the coil itself that we could calculate by, say, doing pi r square on something like this coil that's in that diagram. And if you were in physics, that's exactly what we would do. But now the cool thing is, and we actually call this an EMF, this induced electricity is actually equal to the change in the flux, because remember, over time. So obviously, the quicker I move the magnet back and forth, and you're probably looking at this going, Mr. Cole, what is this EMF? Well, I'll give you a hint. It's measured in volts. So we've still got like a potential situation going on here, but unlike a battery or another source, we're inducing this flow of electricity, or this electromotive force, if you want to call it that. I think one of my favorite examples, though, of induction, and it's used in so much, are these little shake lights. And all you got to do is shake this back and forth. And you ever thought about what you're shaking? Well, what's neat inside here is there's just a magnet inside this thing, a north and south pole magnet, and you're shaking the magnet back and forth inside the coil, and that's what's actually creating the flow of electricity. Now, I think induction is really cool because induction is what we actually use to run, say, a generator. See if I can pull up a generator real quick. This is going to be a short video. But we can use it in generators, transformers, and all kinds of stuff. So notice something. Let's turn my water on. Let's get a little flow of water. And you notice what's happening is it's rotating the magnet. And now you've got a changing magnetic field. And that changing magnetic field is what's actually producing the electricity. And obviously, the faster I can spin this, and by the way, if you're wondering, watch the electrons oscillate. Well, that's what makes this alternating current. And the cool thing about alternating current, thank you, Mr. Tesla, for saying that alternating current is awesome. But what's cool about this alternating current is like we're still using this same basic technology now. Matter of fact, this vibration you see in your wall outlets, if you've ever been electrocuted, you've felt a little buzz. The reason why you felt the buzz is because in our electricity today, that's vibrating at 60 times a second. But this is the foundation of how a generator works. So moving back, and I've got one more thing to add to this, and that's what's known as Lenz's law. But Lenz's law is probably one of the hardest. I'm going to have to actually shoot a video where I demonstrate this some, I think, for you to understand it. But it's one of the hardest things for students to kind of grasp. Because what happens is, let's say, for example, let's go back that little demo. And then we're going to cut it off because I really don't want your brain to explode right now. Yeah, this one. The neatest thing in the world is this. As I move, this is what's neat. As I move this magnet into the coil, look at the direction that the electrons move. So do you notice the direction the electrons move? That movement of electrons, we've already established, moving electrons creates a magnetic field. What's neat is this. As we move the magnet into the solenoid, you induce a flow of current that actually creates a magnetic field that opposes this magnet that's moving into the coil. Now, I'm going to say that again real slow because it is incredibly hard to grasp. As you move the magnet into the coil, you induce a flow of electricity. So we saw these electrons moving down, but that movement of electrons also creates a magnetic field that opposes this magnet. So in other words, as this north pole is moving into the coil, remember, we've looked at this before. If you've got current in a wire, I'm trying to move the compass out of the way, but if you've got current in a wire, that creates a magnetic field. So in this case, a magnetic field with we can look at the little compass needles. So this is obviously the north pole of our magnet that we've created, our north pole of our magnetic field. So what is neat is this. Lenz's law is simply saying that as you induce the current in this wire, the current creates a magnetic field that opposes this magnetic field. So see if this makes sense. Look at the little compass needles. As I move this thing in, as I move the north pole of this magnet in, I'm actually inducing current in the wire, so the coil actually has a north pole operating against the north pole of the magnet. And that's all Lenz's law is. And I can do some examples like with a I guess you could call it a rail gun and some other things. And I'll shoot a video to demonstrate it. One of the things you have in your house right now that takes advantage of this Lenz's law are those GFCI outlets that you have around your house, ground fault circuit interrupters. And they actually work because you've got current going to and from, say, a device, and it is alternating, but I'm simplifying it for this explanation. And so what happens is you're creating two magnetic fields, or two currents with magnetic fields opposed inside here. And as long as these currents match, imagine essentially this. Imagine you had 2 amps going to the appliance. You should have 2 amps coming back from the appliance. But what happens is this. If you have, let's just say this, 1.999 amps coming back from the appliance, the way a GFCI outlet is made, it creates this unbalanced magnetic field and therefore this unbalanced current in the loop. There should be no current in this loop, and it's actually what triggers the disruption of the service and cuts it off. That's what's cool about GFCI outlet. It should actually cut off before you even feel a shock. But what's cool is that's a good example of, again, Lenz's law, and it is very hard to understand. I'll try and shoot some more videos about it. All right, so until next time, I'll see y'all guys later. Bye.